Okay, so here is a big picture. Okay, he's a professor from Stanford, and he is ACM fellow. Actually, just now I even wrote IEEE fellow, and he said, I'm not IEEE fellow. I removed it just now. And his current research interest is basically in database theory, database integration, data mining, and education. So I think a lot of people know him because we studied his textbook, very influential textbook. Could you go to the next slide? So I think if I put these slides, most of you know this because this is he has co-authored more than 16 books. I think recently new books will be available about data mining. And here is several books I put it here. We can see the Dragon books on compilers, Cinderella books on autonomous theory, languages, and computing, and also many, many others. Even still, I put one Japanese translate book there. Okay, and this is so it is so again. Let's review his awards. I put some rate one here. Knuth Prize, called Innovation Award, which is the most prestigious, I think, in database community. Von Neumann Medal, IEEE, even not IEEE fellow, and is also last year he got NEC C&C Foundation Prize, just last October, maybe October. Okay, so I think without further ado, let's welcome Professor Ullman.
Thank you very much, Kitsurugawa-sensei and Hu-sensei, for that very kind introduction. I was very amused to see that picture of me that was actually taken in 1991, I think. It's oddly enough, though, if you noticed, I'm wearing the same tie. Anyway, okay, so I'm not really used to doing this, but I'm going to give a talk that is sort of half political, half technical. And you can see the three questions I wanted to ask you is data science a real thing, or is it like most things that call themselves a science? If it calls itself a science, it isn't, I think is the, see, physics doesn't have to call itself a science, we know it is. So is it real? Is it just machine learning? Is it just statistics? Give you a hint, yes, no, and no. And then I'm going to wax a little bit technical and talk about some examples of some algorithms that don't fit into it's machine learning or it's statistics view of things. And a couple of the algorithms which I hope many of you have seen, but if not, I think it's worth knowing about. And that, I will intersperse the talk with some experiences on something called the Data Science Education Roundtable that I've been part of. It's kind of an interesting experience, and it's actually colored a lot of my views here. So let's see if this goes through, which it does not. I have to turn it on or something. Okay, so along around 2000, actually even a little earlier, we used to call it data mining. Okay, then maybe 10 years ago, 8 years ago, it became big data. And now it's data science. Okay, well, I claim that these are just new names for the same old idea, which is an important one, which is you take the biggest hardware configurations and the best algorithms you can invent and the best programming systems. By programming systems, I'm thinking of things like Hadoop. And you put them all together and you solve problems that people care about. So it turns out that data science has become a very popular subject, and in academia, it matters. You want to claim the things that everybody cares about as if it were your own thing. Quote in English, success has 1,000 parents, but failure is an orphan. I suppose makes a lot of sense. So at any rate, so I will counter machine learning people who, to them, data science is nothing but machine learning. And of course, I don't want to be too critical. Obviously, machine learning is a very important idea these days, and a good, a significant portion of data science can be classified as machine learning. And then if you talk to statisticians, they believe that data science is a branch of statistics. I've heard one of them say it's statistics done right. I don't know. Maybe that's true. Well, again, as they said in the introduction, I'm really come from the database community, and my view of what data science is about is that it's sort of what database people have been doing all along, which is, again, dealing with the largest amount of data that one can handle and solving real problems with it. In the education space, I want to, I feel that the right preparation for, if you want to become a data scientist, and I'm going to talk about this in a little more detail, but it's basically exactly the way we've been educating database people. The core, you get the core computer science education, and you take everybody's got to specialize in something these days. You take special courses that address the various ways that we handle large-scale data. Now, to set the stage, I want to really address the statistician's view. Now, first of all, an interesting story. I did not draw this diagram. Where did I get it? I Googled data science Venn diagram, and it turns out that there's actually a Wikipedia article with that title, Data Science Venn Diagrams. And the first one is this. It's by a fellow by the name of Drew Conway. Now, who is Drew Conway? It turns out he was a graduate, when he drew this at least, he was a graduate student in political science at New York University. So I could easily say, well, what does a political scientist know about computing? But turns out he actually has a bachelor's degree in computer science. But I think more important is that I've seen in at least 2 different venues statisticians showing this diagram as, to them, it explains what data science is about. Now, obviously, I'm a little bit unhappy with this diagram. So let me just sort of go through the problems I have with it. Well, the easiest thing is what he calls substantive expertise. I would call domain knowledge. That is, if you're going to apply algorithms to solve somebody's problem, somebody's got to understand something about the problem. Ideally, it's you, the person who's actually writing the code, but you need somebody who understands the problem. Yeah, okay, so I agree with that. Now, this really drives me nuts. The bubble that should have been labeled computer science, he calls hacking skills, as if the only thing about computer science was you know how to program. Okay, that there's no, all of the work in algorithms and concepts that we've been developing for 50 years or 60 years doesn't matter. It's just, we need somebody to write the code, sure. But there's more. Okay. Now the bubble that I'm pointing to now is what he's saying is it's a danger if you try to solve a problem without the wise guidance of a statistician. Okay. Now I'm going to argue that in fact most of the really important things that we've done in data science really are in that area. Okay, and just to be clear, many of the very powerful algorithms that we use have a strong grounding in mathematics and often statistics. Okay, I have no problem acknowledging that we need their expertise, or we have to learn what they can teach us to do really good algorithms. No problem with that. But again, I'm going to argue that when it comes time to solve the problem, the math, the statistics, they're bundled in the algorithm already. And you don't need their guidance to solve the problem. Okay. But it gets worse. What he describes as traditional research is a combination of statistics applied to a domain with no code at all. And I question, can you really be said to solve a problem if you don't write any code? Now, what I think he means is that the view of the statistician, and I'm going to give you some examples of this, is that what they're really doing is looking at somebody's problem and doing some mathematics about it, but not actually solving the problem. They're just finding the interesting stuff. Okay, and this I find this is a really bad attitude. And last but not least, look what he does to machine learning. It's statistics coded up, hacking, but not applied to anything. And if you're in machine learning, I don't think you believe that that's where machine learning lies. I hope you don't. Anyway, with that, let me just introduce this idea of this data science education roundtable. It's something run by the National Research Council in the United States, is the administrative arm of the national academies. And it, of course, is divided into various branches, and it's the statistics branch that has put this group together. And it's sort of half statisticians, half computer scientists. There's a token engineer and a token mathematician or something. But our job is basically to yell at each other. And we are told not to write a report, so I'm not sure how any of these ideas will get out. But we have been at least investigating what, let's say, what industrial needs for data science education are. We've been talking a little bit about different approaches to curriculum, especially the idea that you have to retrain a lot of people, so you're going to have mid-career education approaches. We're told not to look at the content of individual courses. We're not really a curriculum committee. Okay, well, I haven't really made any friends on this roundtable because my position again is that data science is really squarely a part of computer science. It evolved from the database view of the world, and it just belongs in computer science. And the statisticians, if they want to become computer scientists and play in the game, that's fine. But to imagine that it's a statistics thing, I think is wrong. Okay. So again, I'm fine with the idea that the way you train a computer scientist is you teach them a good deal of mathematics and a good deal of statistics. But I don't like the idea of creating separate units of data science. So you hear various universities are creating departments, or in some cases even schools of data science. Sometimes they call it information science or even library science. I think that is not something that you ought to that ought to be done. It just turns out to be second-rate computer science when it's done. Again, what I would encourage in my position is that within computer science there should be tracks at different levels, sort of the bachelor's level, master's level. At the PhD level, well, you know, you're doing research, so you do if you want to do research in data science, you just do it. I don't think that we need to even think about how a data science PhD differs from a non-data science PhD. But at any rate, the core for computer science, again, in my mind, should include multivariable calculus. You need a heavy dose of that. You need linear algebra. This all plays into data science. Discrete math course, statistics. These are all things, by the way, at Stanford we have always required all of these things, statistics included, for everyone at every level, including the bachelor's level. And then there's a core, a real computer science core, obviously introduction to programming and data structures, and something about, everybody needs to know something about the various software systems. And then if you're going to be a data scientist, I think you need to take the course in database systems. There's a lot of data mining algorithms that were developed. Artificial intelligence has had a resurgence. My guess is that AI is finally here after decades and decades of sort of fake AI is going to take over the world. I think finally it's real. You really do need to know something about AI. Machine learning, obviously. You need to know something about algorithms beyond the typical data structures course. Data wrangling. This is an interesting thing. Wrangling. Anybody know what I'm sure everybody here has taken many years of English study. How many know what a wrangler is? Okay. What is it?
Doing data reprocessing.
No. Well, yeah, data wrangling, yeah. Well, sort of. Okay, but what a real wrangler is? It turns out, I Googled it. It turns out I was misinformed. A wrangler is actually a cowboy who takes care of the horses on a cattle drive. Cows are easy. They're very docile. They do what they're told. Horses, not so much. If you're the wrangler on a cattle drive, you have your hands full keeping the horses under control. And data is kind of like that. It's unfortunately not something that you can teach all that well. It's something you have to do by just give people experience in sort of discovering that they have to deal with the data as it exists, not the way they thought it existed or the way they'd like it to exist. And so I think that's, you absolutely need a practical course where people spend a term or something just wrangling a tough problem, just getting the data to work. Anyway, a number of especially at the master's level, I think there should be a number of options. Natural language processing turns out to be very, very important for a number of kinds of applications. Obviously, parallel processing is coming into its own, and data science applications are a good reason for that. And then there's more of advanced courses. There's more than one machine learning course these days. Lots of AI courses, and of course more statistics. Not a bad idea. And especially at the master's level, I think, you should know something about some application. Okay, you don't have to be an expert biologist or something, but you should know something beyond computer science. That's probably true for everybody. Okay, so what bugs me about the statistics view of things? What I've seen both in the education roundtable and some other opportunities I've had to sort of see statisticians in their natural habitat is that the problem with the statistics view, again, is what it says here, is that they think if they analyze the data, find something interesting in it, that they've solved the problem. But they haven't. The way you solve the problem is you actually solve the problem. So here, for example, one of the things I learned at this data science education roundtable, the statisticians run something called what they call a hackathon, and it's actually become somewhat international. It's not just the U.S. anymore. But to them, what a hackathon is they give teams of students a large data set, and then they say, go find something interesting. And then after 2 days, they come back and the judges decide who found the most interesting thing. Okay. Nobody had to solve anybody's problem. This is what is wrong with the data with the statistics view of data science. In comparison, for many years now, there's been a website called Kaggle. I believe it was just bought by Google, in fact. And on Kaggle, people post real problems, things that they would like to have the community at large solve. They provide the data, they say what how are you going to evaluate a solution, and people don't just go after whatever they find interesting, they go after the problem. This is the right way to do it. Okay, I think. Another thing, another example, we had a discussion of this. There's a startup company that came out of the statistics community that sells people what they call data science boot camps. And they say that they're teaching them data science problem solving. But when they describe what they consider to be a problem solving process, well, it starts off right. You have to acquire your data. Often that's not trivial. You have to clean the data. That's almost always non-trivial. That's sort of the data wrangling problem again. The data is never what you wish it were. You've got to get rid of outliers, possibly restructure it in a way that makes sense. But their last step is produce a model. Well, models by themselves don't solve problems. Algorithms solve problems. But to them, algorithms, nothing. Okay. Now, to be fair, there are some problems where once you've got the model, you kind of have the algorithm. So, for example, if you want to identify spam emails, the key part is how do you model whether an email is spam or not. Once you have that, the algorithm is fairly simple. You just say, for each email, see whether it fits the model for being spam. If it is, report it as spam. If not, send it to the person's inbox. However, there are some problems where the solution doesn't really have an underlying model, and I'm going to give you a couple of examples of that before long. Okay, so let me offer you my data science Venn diagram. Now, I was a little bit hampered by the fact that I only know how to draw circles in PowerPoint. And as a result, things don't come out to scale. It's a little bit embarrassing. But all right, we'll start off. Obviously, in my mind, computer science is a big part of data science. And domain science is also a big thing and part of it. And to me, data science is simply the intersection of these two. Okay, it's computer science applied to domain science. Now, machine learning, as I said, is to my mind a part of computer science. Some machine learning impacts data science. Actually, maybe most of it does. I might even say. Now, where do math and statistics fit in? Well, I think it looks like this. And again, these bubbles, they deserve to be much bigger, but I can't make them bigger without intersecting things I don't want them to intersect. And in particular, what I'm trying to emphasize here is that math and statistics feed into computer science. They don't solve people's problems directly. They only do it through computer science, sometimes through machine learning, sometimes not. Okay, but that's not to say that math or statistics are small things. They're not. They're really big things. Okay. Okay, now, as far as statistics, again, I don't want to at all imply that statistics is not important. For example, if you design a lot of algorithms these days are randomized algorithms, if you don't understand the underlying statistics, it's not clear that your algorithm is necessarily solving the problem you think it is. If you are an algorithm designer, even for algorithms that are not themselves randomized, you need to ask the question, how well does my algorithm perform on random data? That obviously is a statistical question, often a fairly deep question, because what random means may not be terribly clear. I also want to say that there are some applications of data science where where you do need that statistician to pronounce this is correct or not. That is, where you need to assert the statistical validity. Just for example, again, one of the members of this roundtable that I'm on works for the Census Bureau, and countries take censuses, and they will make statements. Statements will come out of the census like 10% of the population of this district is below the poverty level. Well, money is going to change hands because there are going to be political decisions made based on the result of these analyses. So you got to be sure that this is, does 10% mean, well, probably less than half, or does it really mean between 9% and 11%? Again, it's important that we understand that. Another thing the statistics community knows a lot about, sort of the traps that people get into. Just to give you an example, there's been a lot of discussion about using data science to deploy police to what they call high crime areas. Now, intuitively, this makes sense, right? You want the police to catch the criminals. They got to go where the criminals are. Okay. So what happens? You deploy more police to an area that you've identified as high crime, and the crime rate goes up, not down. What happened? Well, the trouble is, again, this is a data fallacy. Everybody should know about this, not just statisticians, but it's important. If the way you're measuring crime is not by actual crimes committed, but by arrests, obviously, when you put more police in an area, you get more arrests. Well, in fact, I mean, to give you actually a concrete example, in New York City, where I was born, they actually had a very serious crime problem throughout the city, and it was stopped, not stopped, but it was, let's say, greatly reduced by a policy that Mayor Bloomberg introduced when he was the mayor. It's called stop and frisk. Again, if you don't live in the United States, you probably don't realize that lots of criminals carry guns around. And what Bloomberg allowed the police to do was to just stop people who looked suspicious for any reason and pat them down and see whether they were carrying a weapon. And interestingly, in New York City, it's perfectly legal to take a gun and walk down the street waving it, pointing it at people. That's okay. What you're not allowed to do is hide it. You cannot have a concealed weapon. I know this sounds completely nuts, right? It is nuts. Okay, it goes far. But that's the way we do it in the United States. Okay. So stop and frisk was actually catching people who shouldn't be carrying guns, and in fact stop crime. Now, a new and very liberal mayor, de Blasio, took over, I think, 2 or 3 years ago, and he stopped the stop and frisk policy. And now he announces, see, I knew I was right. When I stopped the stop and frisk policy, crime went down. But of course, he was looking at arrests, not actual crimes. In New York City, generally when a crime is committed, you don't even bother reporting it because the police aren't going to do anything about it. So there's no way, you don't even have a chance of gathering reliable crime statistics. You have to use arrests as a proxy. But of course, arrests went down because without stop and frisk, you weren't able to catch these people. You know, they kept carrying their guns, and then they used it to hold up somebody on the street. Nobody reported that. Anyway, be that as it may, that's an example of how these things go. Anyway, so what's wrong with the statistics claim that you have to have statistics, you have to know the statistics of what you're doing all the time? Well, I claim that most data science, again, with exceptions like census data, it's experimental. You learn how well your algorithms are doing by measuring the results. So, you know, for example, Google is always worrying about the formula it uses to order the top 10 results. When you send a search query to Google, it would like it that the thing you wanted, it always appears number 1 on its list. But sometimes it doesn't. If you click the first thing, it says, oh boy, we got it right. If you click the 5th thing, then it says, oh, well, we didn't quite understand what it was you wanted. Let's see if we can do better. So they're always experimenting. They're changing their formula a little bit. And they see, does the average rank of the first click go up or down? That's how they learn the right way to select the the responses to your search query. And again, I claim that in contrary to the statistics view, most of the time it's more important to do the best you can and get it done than to determine exactly how well you're doing. Just do, your best is all we're going to get anyway. And one of the things which again I want to remind you of, I have a lot of respect for statisticians. The best ones have taught me things about algorithms. Okay, many statisticians these days are actually inventing algorithms the same as computer scientists. Okay, so let me give you an example. So Google and a lot of sites try to detect an email that is a phishing attack. These things are very dangerous. Okay, well, how good are they? I don't think anybody has any idea. And anyway, even if you had a statistically valid analysis of what fraction of the phishing attacks you are detecting today, the phishers are going to change their plans tomorrow. It's going to be another set of attacks, and your statistical analysis would make no sense. And therefore, while, look, I'm sure that Google uses a lot of good mathematics and good statistics in developing their defense against phishing or detection of phishing attacks, but they don't need a statistician to tell them how well they're doing. Okay, now if you remember, coming back to the Venn diagram, this is an example of something that's in what he called the danger zone. It's an application to finding phishing attacks solved by hacking, by an algorithm. Okay, and again, to call this the danger zone, I think, is ridiculous. The real danger is if you didn't do this, that is, if Google did not do the best it could to catch phishing attacks just because they couldn't analyze how well they were doing. Okay, anyway, there are lots of examples. For example, people are using data to attempt to match treatments to particular patients based on the patient's genome. Again, it's far more important to do the best you can than to say with 90% certainty this is the right treatment. Predicting hurricanes. In the United States, we had a number of very serious hurricanes recently, and they kind of knew roughly where they were headed, but didn't get it 100% right. It was still rather useful to do the best predictions we could. And again, even the more mundane things like predicting which ad to show you, or recommending a movie based on the movies that you've seen previously. Okay, so now I've sort of picked on statistics enough. Let's talk about machine learning a bit. Okay. Okay, and let me again start by conceding. Many problems are solved by machine learning. It's a really important branch of data science. And in situations where people have been able to compare machine learning approaches versus non-machine learning approaches, the machine learning approaches usually win. And I'll give you just give you an example. On the other hand, how many have seen these Gartner diagrams? These are, it's always fun. Every year they come out with a new one. I don't know how much of this you can see. I can see absolutely nothing on the screen in front of me. But if you look up here at the very top of the hype, again, the whole idea is a field of interest. It gets hyped higher and higher and higher. People think it's going to solve all the world's problems. Then it hits the top of that peak there. Then they realize it's not going to happen, so they just give up on it, and that you hit the trough, what they call the trough of despair. And then good scientists come along and they kind of figure out that there really is something in there. They make it work where it can work. It never quite lives up to the hype, but something good comes out of it. So look at what's at the top there. It's machine learning, and even higher, at the very tippy top, is deep learning. Okay, so so right away I'm kind of, you know, machine learning can't be that good. Is my theory. So again, with all due respect, if there is something, machine learning will eventually hit the asymptote where it will be an important tool in our arsenal of things that we use to solve people's problems. Well, I get a little bit nervous, and I've had some discussions with machine learning people who, whenever I point out an idea that is clearly not machine learning, like locality-sensitive hashing, which I want to talk about, that when they said, well, it must be machine learning. Why? Their argument was, because it's a good idea. Complete nonsense. So here's some examples. Clustering is now called unsupervised learning. Well, people were talking about clustering long before there was a machine learning community. Gradient descent, likewise. This is something, I think it goes really back to Newton's approximation for derivatives. Association rules are something I'll talk about. Again, I assume most people are familiar with them. Clearly, a data mining technique that did not come from the machine learning community is often classified now as machine learning. The second objection, again, which I will talk about by giving you a couple of examples, is that not every data science problem is the search for a model. Okay. And so there are things which machine learning just does not, is just not an appropriate tool. And the third is, even in situations where you do want a model, understandability counts sometimes. Okay. And I'll talk about that, I guess, actually immediately. Okay, so let's talk about association rules again. Well, they're just if-then rules that you construct by looking at your data and sort of counting co-occurrences. And again, it was Rakesh Agrawal, and a number of his associates in the early 1990s that developed these ideas. They did not think of it as machine learning, and I think it really isn't machine learning. So just as an example, if you wanted to use association rules to develop phishing attacks, the way you would probably do it is you would look at the words. Well, you'd presumably you know certain emails have been labeled as phishing attacks, others have not. That's your training set. It's sort of just like machine learning. And you discover rules of the form that if the email has some combination of words, then it's a phishing attack, or if it has some combination of words, it's not a phishing attack. So, for example, Nigerian and Prince, pretty good bet it's a phishing attack. They're often called Nigerian Prince attacks. I assume everybody knows about this. Now, the fact is that association rule model, basically you're building a model, but it's a very rudimentary one. And even just very simple and naive Bayes machine learning models, where you might, for example, put a positive or negative weight, or learn positive and negative weights to put on words. For each email, you sum the weights of all of its words, and if say the sum of the weights is greater than 0, you declare it phishing, and otherwise not. Even that kind of a model will be much more reliable than, or somewhat more reliable than the best that you can get out of association rules. But if understandability matters, association rules are clearly understandable. That is, so if a Nigerian prince, sends calls up Google, they have to call up Google because you can't get any emails through, right? If Google were using association rules, they could say, well, here's the reason, Your Majesty, why your emails aren't getting through. It's because you say you're a Nigerian prince, and we know you are a Nigerian prince, but we have this rule that says if you say Nigerian prince, we don't send your email. So at least you may not like it, but you can understand it. Now, I don't know if you've ever asked Google why it classifies something as spam, but it says something like this. It says, because it looks like other emails that that have been reported to us as spam. And all that means is, well, we have some model, we can't explain to you what it is, we probably don't even know what it is ourselves exactly. But our model says it's spam. Now go away and it doesn't matter, right? Because it's all you care is that you don't have to see the spam emails, and yet you don't have important emails winding up in spam. And that's fine, and let them do their thing. Now, on the other hand, insurance companies are rating you for automobile insurance, life insurance, or medical insurance. They're building models of the whole population, and they're classifying you some way, and they may change how you're classified. And and you wind up paying a higher premium, and you don't know why. You're the same person. Okay, but the model has changed, and if these some very sophisticated machine learning models, there's no way they can explain. There's a million parameters that they've learned, and you put them all together, and it says you've got to pay more money. So again, my position on where machine learning is proper, well, first of all, it's got to be one of these problems where you need a model. Fair enough. You don't need a model, you're not going to get, you don't want to use machine learning. And then there's the explainability issue. It better be something where you can get away with a model that's unexplainable. And again, sometimes you can. Like email spam. But I think it also has to be something that you don't yourself understand well. My favorite example is there was a fellow who graduated from Stanford, actually started a little company called Jung Lee. They were doing information integration, and they hit it just right. The guy became rich. Decided to start a company doing machine learning. This was back in the 1990s. Started a company called Whiz Bang Labs. He actually hired some of the best machine learning people of the day. And their first goal was to machine learn how to identify people's resumes on the web. The idea was they were going to do a job search service. Well, the fact is that they went bankrupt And I think the reason they did it is because they never really were able to beat the obvious. See, the trouble is, we all have resumes, and we kind of know, because if you don't know, your friends will tell you what you put in a resume, what you say, what you don't say. And so we all have kind of an understanding of how resumes work. And, people were writing, just off the top of their head, writing code that was doing as well as the machine learned algorithms for finding resumes. So they really had essentially nothing. Anyway, now we've got, I guess, about 15 minutes left. We'll do the. I just want to give you a little bit of technical comments, and in particular, two examples where algorithms that are clearly important in for many big data science algorithms that don't involve models. One is locality-sensitive hashing, and the second is the Flageolet-Martin algorithm. Anyway, while I'm up to it, I just want to remind you, if you haven't found it, there's a free book that we have we put up on the web. There's the URL for it. Mining of Massive Data Sets, MMDS. You can learn about these two algorithms and a lot of other things if you care to. I don't expect you to be able to remember this this URL, but the same authors have a MOOC running off at Stanford. People are welcome to take that. It's asynchronous. You can start at any time. And we will actually, if you successfully complete the course, we will actually give you a piece of paper. We'll give you the bits that you can print on a piece of paper. We don't actually give you the paper itself. Okay, so locality-sensitive hashing. The idea is there are problems where you'd like to, you have a fairly large set or a very large set, and you'd like to find those pairs of items in the set that are similar. And there are lots of applications. I'm going to focus on one. It's called entity resolution. It's a very common problem. So we're given a collection of records, and these records refer to people. So there'll be a field like the name, their phone number, their address, email, URL, whatever, just information. But for a variety of reasons, things don't always look the same. Well, for example, people entering names make typos. Okay. They get confused as to what's your family name, what's your given name. Okay. People change their phone number. Right? You may have had a phone number and you discontinued its use, and that gets given to someone else. So you have two people who are different, but they have the same phone number. So it's a little bit tricky to decide which records really refer to the same person. Now, the trouble is, even if we had an algorithm for deciding whether two records refer to the same person or not, even a relatively small data set, like 1 million records, there are 500 billion pairs of records, and to compare, to run this algorithm on 500 billion things is a monumental job. Okay. Okay, and again, I might comment that this is not a problem of modeling. Okay, you could say, well, you need a model to say whether two records represent the same person or not. Maybe that's true, but that's not the hard part. The hard part is, how do you find the pairs that do represent the same person without looking at all, let's say, 500 billion pairs? Well, the idea is that you can get better than the obvious. There's where if you have n records, you have about a half n squared comparisons to make, as long as you're willing to accept a few false negatives, that is, pairs that are similar but you don't notice them. You can do a lot better than order n squared. And the way you do it is you need several hash functions that have a property which, when you think about it, is kind of remarkable. It says, if two items are similar, there's a good chance they'll get thrown into the same bucket. But if they're not similar, then they're going to be distributed at random. The chances of their appearing in the same bucket is almost zero. Okay. And now we're going to run many hash functions like this. We will only compare two items if they wind up in the same bucket for at least one of these hashing. And again, if you tune the numbers right, you wind up with the buckets tend to be very small, except when they contain things that are in fact need to be compared because they are similar. So again, when you think about that, that seems almost too good to be true. But in fact, it isn't. For example, hash to buckets based on the name. Okay. If two records have the same name, then there's a fairly good chance that they're similar. And in particular, if they're similar, there's a fairly good chance they'll have the same name. Yeah, they might not. There could be a typo, or you left out the middle name in one and you included the middle name in another. Lots of reasons why that might not happen. So you do another hashing, let's say on the phone. Okay. If two records have the same phone number, there's a good chance they refer to the same person. Again, it might not be the case. Could be a typo, could be a phone number that's been recycled. And you keep doing this for any number of fields. And you do have this property that if the records are similar, there's a much better chance that they will wind up in the same bucket than if they're not similar. Okay. So what you hope is that two records, if they are in fact similar, they'll wind up in the same bucket at least once. And you can then go and test them to see if they're really similar or if this was just some freak accident. What you hope is that if records refer to different people, they will not have the same name, they won't have the same phone number, they won't have the same address, and so on. Again, so as I said, you have to look at what's in the buckets, because just because things are in the same bucket doesn't mean that they're similar. You do need some tests to examine the records as a whole to see whether they deserve to be considered similar. Okay. Anyway, the other thing I want to talk about is approximate counting. Now the model is they have a stream of elements coming in, and what I want to know is how many different elements are there. So a good example is people logging onto Facebook. Every time you log onto Facebook, Facebook makes a record of the fact that you logged on, and they always want to report how many unique users were there in a month. Well, one way to do this is to just keep a hash table. A new name comes in, you hash it, you see whether it's already in the hash table. If not, if it is there, you just ignore it as far as this, as far as the count is concerned. If it's not in the hash table, you put it in the hash table, you add 1 to your count. Okay. That'll give you an exact count, but of course you need a hash table. If there are 2 million items and each is 2 billion Facebook users this month, and each one has a name, let's say 25 characters. On average, we're talking about 50 terabytes for the size of the hash table. That's a lot. Another example where the hash tables are small, but there are so many of them that, again, it's kind of prohibitive to do things right. Okay, so if you've ever thought about how let's say, Google or Bing do their web crawling, they visit pages. The pages have outlinks. They follow the outlinks, but there are too many pages to catalog them all. So they would like to visit the high page rank pages first. Why? Because those are the ones that people would actually see in response to a search query. If you're going to have a page that has an incredibly low page rank, nobody's going to see it anyway. It doesn't matter whether you catalog it or not. Okay. Well, the problem is because you can't tell whether a page has a high page rank until you've finished your crawl. One way to approximate it is to say, I'm going to just visit pages that have a large number of inlinks. Those are the ones that will tend to have a higher page rank. There's no guarantee, of course. So what you want to do is you want to count the number of distinct inlinks, the number of distinct predecessor pages in the graph of the web for each page that you visit, or might want to visit. Okay, so the problem is, again, that you want for each of the, let's say, trillion or many trillions of pages, you want to count the number of distinct inlinks that you find. And again, I claim that in this case, an approximation is just fine because it's just a heuristic anyway. You're trying to prioritize which pages should we actually look at and see where their outlinks go, and which should we just forget about. Well, there's a technique called due to Flagellé-Martin that lets you get an approximate count and in fact uses a lot less space than the obvious algorithm. And again, it's just an approximation, but the more space you use, the better the approximation will be. So you're going to keep a number of what we call variables, say 100 of them, and each variable is a small integer, and I mean a really small integer, like 5 bits, is up from anything from 0 to 31. That's fine. Now for each variable, you're going to have a hash function, and the hash function is going to map inputs to bit strings. So let's say if you're Facebook, you're going to map user's Facebook name to bit strings. Now the tail length of a bit string is just the number of consecutive zeros at the end. So half the bit strings end in 1, they have a tail length of 0. Quarter of them end in 1, 0, those have a tail length of 1, and so on. And then I just want this variable v, that's associated with one of the, say, 100 hash functions, will recall the largest tail length seen so far. Now, the cute thing is this. If the largest tail length you've ever seen is r, then 2 to the r is a good estimate of how many different values you've seen. Well, think about it. If you've seen 2 to the r different values, then the chances are good that any tail of length r, including the all zeros tail, will have been seen. Probability is 1 minus 1 over e, about 68%. So that just give you an idea that 2 to the r is going to be a good estimate. Well, it turns out to be, it's a little bit more complicated than that. You have to combine the estimates of, let's say, the 100 different hash functions and their variables. So you need to combine them in a fairly tricky way, and it's in the book. I'm not going to go into it here. So what did I want to tell you? Well, again, first of all, the data science to me is a natural evolution of the work that has occurred in many branches of computer science to impact sciences and industry. Again, statisticians are, again, they sort of got it right, but they're a little too focused on entertaining themselves with analysis of data rather than solving problems. And again, machine learning, big part of data science, definitely not the whole thing.
Okay.
Okay. Right on top.